Hi everyone. This lecture is going to be about variables and distributions. In the previous lecture we discussed variables. We introduced and described the different types of variables, for instance ratio, continuous, ordinal, dichotomous, and nominal variables. An important thing to consider in statistics is that the variables we're typically interested in statistics are so-called random variables. So the key word are that these variables are random. So it doesn't necessarily make sense to really think about a particular value of these variables. So you might be asking yourself, then how do you talk about these random variables? How do you describe random variables? How do you talk about the properties of random variables? So in this lecture we're going to discuss the implications of random variable, and we're going to describe the method or the actual quantity that's useful in describing what a random variable's behavior is. So that's this so-called distribution. We're going to look at the differences between an empirical and a theoretical distribution, and we're going to introduce some of the important attributes of distributions. So we're going to talk about mean, median, mode, standard deviation, and in the next lecture we're actually going to nail those concepts down in more detail. So random variables. The interesting thing in statistics is that the variables we look at can vary randomly. This is maybe different than the typical types of variables you're used to encountering, and this is actually interesting and it's very useful. So an example of the behavior that a random variable exhibits is that every time you observe it, its value is going to be different. So take blood pressure, for instance. If we take different blood pressure measurements, each time we're likely going to get a different number just due to random variation. So the different types of random variables that we're going to talk about, and the different types of distributions that describe these random variables, are going to be the so-called discrete random variables. So discrete random variables are random variables that can take only a countable number of values. So the dichotomous and categorical variables that we were looking at last time would be considered discrete. So some examples of those would be smoker versus not, so smoking category, disease versus not, so disease category. Even a variable like, say, the number of new infections would be discrete because it can only take a countable number of possible values. For instance, 0, 1, 2, 3, all the way up to potentially infinity. For continuous random variables, which I've denoted here, these type of variables can take any value in some interval. So for instance, height, weight, systolic blood pressure, diastolic blood pressure, and others. The point here is that the types of values that this random variable, a continuous random variable, can take are very dense. So let's talk about some of the characteristics of a random variable, and maybe it'll help if we first look at mathematical relationship versus a deterministic relationship. So what you'll see in this first bullet here is a mathematical relationship that I've written, and it's y equals mx plus b. So you probably recognize this type of equation from your college algebra class, and it's essentially a mathematical relationship that describes a straight line. So given an x value, if you know the values of the slope m and the intercept b, you can produce a corresponding y value. So if you gave me a bunch of these x values, you could plot the corresponding y values, and the points would fall on a straight line. Okay, that's different from this notion of a statistical relationship. And what you'll see here is I have something that's written, it's relatively similar, y equals alpha plus beta times x, but I have this additional term out here, epsilon. And what this epsilon is supposed to signify are random deviations of these points around a straight line. So let's see if we can look at a statistical relationship versus a mathematical one. So let's change the color here. So if this is our coordinate system, this is our x-axis, and this is our y-axis, then a mathematical relationship would look something like this. So we may have a straight line y equals mx plus b. So any point x on the x-axis corresponds to a point here, a y point, and you get the pair x naught, y naught. So I'll just write underneath a mathematical relationship. And for a statistical relationship, I'll draw the same type of axes. So I've got my x-axis, my y-axis. I'll again draw a straight line. So this equation is y equals mx plus b. But for a statistical relationship, the points that I'm going to draw aren't going to fall exactly on this straight line. So if you had a set of observed data, a set of xy points, they would deviate from this straight line by an amount epsilon. So this would say be epsilon 1. This deviation might be epsilon 2, all the way up to the last deviation, epsilon n. So a statistical relationship essentially lets you see that there may be some underlying straight line, but your y deviates randomly from this straight line. We're going to talk more about this type of model when we get into regression. Okay. So these sources of variation can be biological, they can be measurement error, as we've discussed before, they can be random variation, etc. And so since statistics is concerned with variation, we want to be able to measure, describe, explain, and potentially control this variation. So we said we were going to talk about distribution, so let's talk about this first concept that I'm calling an empirical distribution. So an empirical distribution, or a histogram, is essentially the sample estimate of the underlying true population distribution. And you can compute or draw this empirical distribution by binning up the values of your particular random variable and counting the number of occurrences in each bin. And so a histogram can help visually assess where the mean is, where the mode is, the median. It can give you an idea about how variable is the data, how much variation is in the data. It can tell you about percentiles, quantiles, the skewness of the distribution, whether or not the data looks approximately normal, etc. So what we have here in this figure is the empirical or sample, these mean the same thing, empirical or sample distribution of the frequency of serum total cholesterol levels in a sample of 71 subjects. So what we have here on the x-axis of this plot are the different serum levels of cholesterol, and the corresponding y-axis here is the number of times in the data that each particular serum cholesterol value was observed. So for instance, this point here would indicate that this cholesterol level was observed 4 times in the data. So 4 people had that cholesterol level. Similarly, this value here would indicate that 3 individuals in the data set had this cholesterol level. Okay. So this is another depiction of that same empirical distribution, except that we've used a different level of binning. So instead of looking at individual whole number values of serum cholesterol on the x-axis, we've binned the x-axis into these categories. So serum cholesterol less than 130, serum cholesterol between 130 and 149, serum cholesterol between 150 and 169, serum cholesterol between 170 and 189, between 190 209, between 210 and 229, and greater than or equal to 230. And what we have here on the, again on the y-axis, are the number of individuals in that data set in each of these categories, in each of these bins. And you can see that this data looks approximately, so if I were to actually draw an estimate of the density, this data looks approximately bell-shaped or normally distributed. So what I have here is a schematic or a picture of one of the most common distributions in statistics, and this is the so-called normal or Gaussian distribution, and it's named after Carl Friedrich Gauss, who described this distribution. And in this particular picture, we have a normal distribution with mean mu and standard deviation sigma. So we're going to describe more about what these measures of central tendency, for instance mu, and what these measures of dispersion, sigma, mean, in more detail later. But essentially what this mu tells you is it gives you an idea of location. It tells you where this distribution, this normal distribution, sits at. And this standard deviation gives you an idea of how dispersed this distribution is. So for instance, if sigma were to get larger, then the curve or the density function of this Gaussian distribution would become flatter and flatter, eventually flattening out to a horizontal line. If this sigma gets smaller, then the curve of the normal distribution gets more and more peaked. So essentially you have less and less variation. Everything would be concentrated more around the mean. And the mean, for instance, if you were to increase the mean, it would shift the entire distribution in this direction. If you were to do a decrease in the mean, it would shift the entire distribution in this direction. So importantly, we can describe the areas between standard deviations of the normal distribution, and this is going to become even more important when we talk about how do we form confidence intervals and why do we use particular values like 1.96 when we form a 95% confidence interval. So for the normal distribution, what you'll see I have written down here in the caption is that 68% of the area is within 1 standard deviation of the mean. So what does that mean? That means the area under this curve within 1 standard deviation of the mean is approximately 68% of the area, of the total area underneath the curve. So I'm going to shade in all that. Of course, you know, you can probably guess, since this is a distribution and we have to, it has to actually encompass all the possible values of the random variable, that the total area under the curve, so for instance, if you could calculate all the area going from way back here to the negative numbers and then way up here to the positive numbers, the total area underneath this curve should be 1, or 100% of the area. So for the Gaussian distribution, 68% of that total area is within 1 standard deviation of the mean. Approximately 95% of the area, so let's take this away. Approximately 95% of the area is within 2 standard deviations of the mean. So that would be this area. So I'll write approximately 95% of the area under a normal distribution is within 2 standard deviations of the mean. And then finally, we'll take this off. And then finally, virtually all of the area, so 99.7%, is within 3 standard deviations of the mean. So if we were to go out 1 more standard deviation, so minus 3 standard deviations and plus 3 standard deviations, and we were to shade in all the area between that, that would account for approximately 99.7% of the total area underneath the normal curve. So why is the normal or Gaussian distribution so important in statistics? Well, the primary reason, and you may have heard of this before, is the central limit theorem, so abbreviated CLT. One thing that I do want to point out before we move on is there's a lot of confusion about what the central limit theorem is. So it's a huge source of confusion in applied statistics. So I guess first I should say what the central limit theorem doesn't say. So in the second bullet, what I have is the central limit theorem does not say that your data becomes normally distributed as the sample size gets large. And here's a case of that. If you start out with binary or dichotomous random variables, so those are, remember, variables that take values 0 or 1, that data can never be normally distributed. How can a dichotomous random variable ever become normally distributed regardless of how much data you collect? So the distribution of these individual data points will always have to be a random variable or correspond to a random variable that takes values 0 or 1, so it's not even continuous. So again, I'll repeat, the central limit theorem does not say that the distribution of your data becomes normal as the sample size gets large. However, what it does say is that sample averages or means become normally distributed as the sample size increases. So the central limit theorem is a statement about sample averages or means, not about the original data generating process. And the central limit theorem says that Averages, regardless of the kind of data you take the averages from, will be approximately normally distributed. So let's talk about parameters versus statistics. So we've introduced the term parameters already, and I just want to re-emphasize that parameters are unknown quantities and they're associated with the underlying population or the distribution of the underlying population. And we've already introduced one of these terms, this term mu, and if you recall, we typically let Greek symbols denote population parameters. So mu is a common one to denote the underlying population mean. Sigma squared is another common population parameter term to denote variance. Okay, so what about statistics then? So statistics are the quantities that you actually compute from the data in order to carry out estimation or hypothesis testing. So X bar, which would be the sample mean, is a statistic. A statistic is a quantity that you compute from the data. A statistic is random. A population parameter is not random. These are fixed, at least if you're a frequentist, these are fixed unknown quantities. Another popular statistic is this S squared, which we're going to let denote the sample variance. And you'll see in this very last note, this last bullet that I've made, that statistics are random variables. These are the things that vary depending on the data set, not your underlying population parameters. Unless you're a Bayesian. So conclusions. In this lecture we discussed how random variables and data are described by distributions and empirical distributions. In the next lecture we're going to introduce important measures for describing distributions. And these are the measures of central tendency and variation. Thank you.